Imagine you're sitting by a campfire. The closer you get, the hotter it is. Simple, right? It's one of the first things we learn about heat. Now, what if I told you that in our own solar system, the biggest campfire of them all seems to play by a different set of rules? With the sun, the atmosphere above its visible surface is hundreds of times hotter than the surface itself. We're talking a leap of millions of degrees. This isn't science fiction, it's a genuine astrophysical puzzle that has stumped scientists for decades. It seems to defy a basic law of nature, so how does our star pull it off? Today, we're peeling back the layers of this seemingly impossible object to understand the bizarre physics that power our world. The normal sun. To grasp just how strange this is, we first have to understand how the sun should work. On the surface, it seems straightforward. The sun is a gigantic ball of hot plasma, mostly hydrogen and helium, so massive that it accounts for a whopping 99.86% of all the mass in our entire solar system. It's held together by its own immense gravity, creating unimaginable pressure and heat at its core. This core is the sun's engine room. Here, the pressure is estimated to be 250 to 300 billion times the atmospheric pressure on Earth, and the temperature is a staggering 15 million degrees Celsius, 27 million degrees Fahrenheit. In this cosmic furnace, nuclear fusion relentlessly crushes hydrogen atoms into helium, releasing an unbelievable amount of energy every single second. This energy begins an epic journey outward. First, it has to get through the incredibly dense radiative zone. Here, particles of light called photons bounce from atom to atom in a chaotic random walk so convoluted it can take anywhere from 100,000 to a million years for a single photon to escape. As it travels, the temperature gradually drops to about 2 million degrees Celsius. The next layer is the convection zone. Think of it like a pot of boiling water. Hot bubbles of plasma rise over 200,000 kilometers, carrying heat to the surface, where they cool and sink back down in a constant churn. Finally, we reach the part of the sun we can actually see, the photosphere. This is what we call the sun's surface. And after a journey of hundreds of thousands of kilometers from a 15 million degree core, the temperature here is a relatively cool 5,500 degrees Celsius, about 10,000 degrees Fahrenheit. So far, this all makes sense. Hot core, cooler surface. It follows the rules. But the sun, it turns out, is a rule breaker. The impossible leap, just above the visible surface, the sun's atmosphere begins. And this is where things get weird. The first layer is the chromosphere, where the temperature starts to climb again, rising from around 4,000 degrees Celsius to 20,000 in just a few thousand kilometers. It's a strange reversal, but it's nothing compared to what comes next. Above the chromosphere lies the corona, the sun's ethereal, ghostly outer atmosphere that we can only see during a total solar eclipse. And the corona is impossibly, outrageously hot. The average temperature of the corona is between 1 and 2 million degrees. That's over 300 times hotter than the surface it's floating above. In some regions, especially during a solar flare, it can even soar to 10 or 20 million degrees, briefly becoming hotter than the sun's own core. This is the coronal heating problem, one of the biggest mysteries in solar physics. It's like standing a mile away from a bonfire and getting scorched, while the person right next to it is just warming their hands. Energy is supposed to flow from hot to cold, not the other way around. So, what invisible force is supercharging the sun's atmosphere? To find the answer, we had to get closer. We had to touch the sun. The prime suspect for a long time, the primary culprit behind this impossible heat was thought to be the sun's powerful and chaotic magnetic field. The sun isn't a solid body, it's a fluid ball of plasma that rotates faster at its equator than at its poles. This uneven rotation twists and tangles magnetic field lines, building up immense tension. These tangled fields, generated deep within the sun, rise to the surface and burst through as the dark patches we see as sunspots, areas of intensely concentrated magnetic activity. These magnetic field lines loop and stretch far out into the corona, storing phenomenal amounts of energy. A leading theory, proposed by physicist Eugene Parker in 1988, was that the corona was being heated by a constant storm of tiny, individual explosions called nanoflares. The idea was that when these tangled magnetic field lines suddenly snap and reconnect, they release a burst of energy. While each nanoflare would be too small to see from Earth, their combined, relentless popping could collectively heat the corona to millions of degrees. It was a brilliant theory, but proving it meant flying a spacecraft right through this magnetic storm. The smoking gun entered NASA's Parker Solar Probe. Launched in 2018, this mission was designed to do the impossible, fly directly through the Sun's corona. Protected by a revolutionary heat shield, Parker has been looping ever closer to the Sun, braving extreme temperatures to taste the solar wind and measure the magnetic fields directly. And it found some incredible clues. As the probe flew through the solar wind just outside the corona, its instruments detected frequent, S-shaped kinks in the magnetic fields, which scientists dubbed switchbacks. For a while, it was thought these switchbacks might be the key, releasing their stored magnetic energy and heating the surrounding plasma. However, more recent data from the probe has shown these switchbacks are common in the solar wind, but not within the corona itself, suggesting they don't form there and can't be the direct cause of the heating. The answer likely isn't a single mechanism, but a combination of factors. The leading candidates are still magnetic reconnection, perhaps in the form of nanoflares, and the dissipation of various kinds of magnetohydrodynamic, MHD, waves that ripple up from the surface. Parker's data has found evidence for both, showing that the corona is a far more complex and dynamic environment than we imagined. The mystery isn't solved, but Parker is giving us the pieces to put the puzzle together. Why it matters solving this puzzle isn't just for cosmic curiosity. Understanding the corona is a matter of planetary security. The same magnetic explosions that may heat the corona also power solar flares and coronal mass ejections, CMEs, colossal eruptions that hurl billions of tons of magnetized plasma into space. If a powerful CME strikes Earth, it can wreak havoc on our tech-heavy world. The most intense geomagnetic storm in recorded history, the 1859 Carrington Event, slammed into our planet with incredible force. It was so powerful that auroras were seen as far south as the Caribbean and Cuba, and telegraph systems across Europe and North America failed, with some operators getting electric shocks as sparks flew from the equipment. At the time, it was a spectacular anomaly. If a Carrington-level event happened today, the consequences would be catastrophic. Studies have estimated that it could overload power grids, causing continent-wide blackouts that might last for weeks or months. It could fry satellites, disabling global communications, GPS, and financial systems. The estimated economic cost in North America alone could be anywhere from a few $100 billion to over $2.5 trillion. We live with a star that, while essential for life, is capable of throwing a tantrum that could knock parts of our civilization back to the 19th century. By understanding the magnetic engine of the corona, we get better at predicting this space weather and protecting our fragile infrastructure. The sun is the source of all life on Earth, a comforting presence in our sky. Yet the closer we look, the more alien and paradoxical it becomes. It is a place where the core is a 15 million degree furnace, the surface is a cool 5,500 degrees, and the atmosphere above it inexplicably screams back up to millions of degrees. This paradox isn't a mistake, it's a fundamental feature of how stars like ours work, driven by the incomprehensible power of magnetism. Probes like the Parker Solar Probe are finally giving us the data to tackle this decades-old mystery, revealing a complex dance of magnetic explosions and plasma waves. Our star is not a gentle giant. It is a chaotic, violent, and impossible nuclear furnace. And as we slowly unravel its greatest secret, it's a humbling reminder that even our closest cosmic neighbor is still full of profound mysteries, pushing the very limits of our understanding. The sun's corona is a puzzle we're just beginning to solve. What other cosmic mysteries do you think are waiting to be discovered? Let us know your thoughts in the comments below. And if you want to keep exploring the biggest questions in science, make sure to subscribe and hit that notification bell so you don't miss our next journey into the unknown. Thanks for watching.